So we talked about Newton's first law, which governs all situations where the net force is zero. Newton's second law deals with all the other situations where the net force is anything other than zero. Okay? So in all situations governed by Newton's second law, the object will be doing what? Not just moving, accelerating. Okay? An unbalanced or net force is going to cause an acceleration. Okay? That is what Newton's second law says. Okay? We've got it written like this right here, but it's actually F net equals mass times acceleration. Okay? If there is an unbalanced force, okay, then the object will accelerate in the direction of that imbalance. Net force is also a vector quantity. Okay? We talked about in the last lesson here that it's the vector sum of all the forces. So are you still going to have to do vector addition? Yes. Okay. It's just now, instead of the units on the vectors being meters, now they're going to be newtons, okay, which is the units for force. Everybody follow me there? All right. So it doesn't change what we do. You're still going to find x and y and find their totals and all that. That won't change. It's just your end result will now be a force instead of a displacement or a velocity or something like that. Okay. All right. So the relationship between force, net force, mass, and acceleration is this. Bigger F net is, the bigger acceleration will be, because mass doesn't usually change. Now, if I have two different objects, one that has a mass of 10 kilograms and one that has a mass of 20 kilograms, and I apply the same force to them, what will the accelerations look like? How much slower? Half, exactly. Which one will be slower, the smaller mass or the bigger mass? The bigger mass, right. Okay, and again, that comes back to what we were saying about mass being the most important safety feature. Okay, the more of it you have, the smaller your acceleration will be because of this. Okay, if I manipulate this to solve for A, it says that my mass has an inverse relationship with acceleration. The bigger M is, the smaller A will be. Right? Sorry, say that again. You said they were going the same speed, and then you said. No, I'm not. That's velocity. I'm talking acceleration. Nope, shouldn't be. If your speedo says they're both going 120, they're both going 120. Okay, mass doesn't affect your velocity. It only affects your acceleration. So when I try to stop the Gulf, it'll stop faster. Okay, because if I apply the brakes, they should be able to stop that smaller mass much more quickly, right? Now, obviously, on bigger vehicles, we put bigger brakes, but I mean, if it's a really slippery road and they lock up, my truck is going to slide a lot further, yeah, because it's got more mass. And so there's a place where maybe that doesn't work out so well for me, okay? But I'll take my chances for when I hit something, okay, that it does work out well for me. All right, so that's one of the things we need to understand. The bigger the mass, the smaller the acceleration. The bigger the force, the greater the acceleration. This says there's a direct or linear relationship between force and acceleration. Okay, the bigger the force, the greater the acceleration will be. Right, and that only makes sense. If I just kind of push somebody lightly with one hand, they don't accelerate very much. If I wind up and get them with both, okay, they're going to accelerate a lot. All right, so does that make sense? This idea of the relationship between force and acceleration and mass and acceleration? Everyone's okay with that? Okay. All right, so Newton's second law deals with what happens when there is a net force. Okay, when there is a net force, okay, then there's going to be an acceleration. So if we go back to that hockey puck example, okay, then the force that is applied to the puck will cause the acceleration as long as the force is acting. Okay, the second that puck leaves the stick, the force is gone. The acceleration will stop. Okay, or in the real world, the acceleration will become negative because now there's all the drag forces that are starting to slow the puck down. Okay, does everyone kind of follow me on that? Okay, this is where sports science comes into play. All right, a little bit of work energy theorem, but a lot of Newton's second law here. If the speed at which I can shoot a puck is influenced by how much force I can exert, then one way to shoot the puck faster is to get, okay, is to have it stay on the stick longer, or for me to get stronger, exert more force. Okay, I either need to exert more force or I need to exert that force for a longer period of time. Okay, now obviously sports science has come a long way, okay, since I was an athlete. Okay, it was just about, okay, get a little faster, get a little stronger. Okay, and that was kind of everything. Okay, now there's so much stuff to do with technique, okay, that athletes are far better able to do things now than they were 20 years ago or longer. Okay, everyone follow me on that? Okay, so if I'm looking at a hockey stick's design, sorry, Counselor.
So why haven't like the speed of a shot changed?
Well, it's changed, and accuracy has changed, okay, because of the design of a stick, right? When I was in high school, a hockey stick was a chunk of tree, okay? They were all wood, okay? That's what sticks were made out of, right? Now, sticks, the handles are made out of one material, the blades are made out of another, okay? They're made out of these composite materials that can do what? They can flex, okay? And the ability to flex is a two-edged sword, okay? The ability to flex does mean that instead of what I get with a wooden stick, which is an arc like this, okay, because a wooden stick will flex a little bit, but not as much as a composite stick will, okay? This here, this arc is the distance over which I can exert my maximum strength on the puck, okay? If I'm using a modern stick that has more flex, that arc's a lot bigger. So if I can accelerate that puck now over that distance instead of the shorter distance, the puck goes faster when it leaves the stick. Okay, the double-edged sword to a composite stick is always at the most inopportune time, is when they decide to self-destruct. Okay, you're winding up, you got a wide open net. Okay, it's a tie game, it's overtime, you need to hit this shot. That's when your stick explodes. Okay, and then the other team goes down and scores because there's nothing you can do to stop them because you're flat on your face because your stick exploded. Okay. Everyone follow me there? Okay, but they do flex a lot more. So as a result, okay, if you have good technique, if you have bad technique, it doesn't matter how good a stick you have, okay, but if you have good technique, you should be able to shoot the puck faster now than you could years ago using a wooden stick. The other advantage is a composite stick is way lighter, okay, so you're not wasting a bunch of your strength accelerating the stick, okay, you just accelerate the puck, right, whereas a big wooden stick was a lot heavier. Right. Same is true for like golf clubs and things like that. Okay. Back in the day, I mean, they still call like the drivers, they still call those woods, like a 3-wood, a 5-wood, because back in the day they were actually made of wood. Okay. Now they're made of like titanium and graphite and all these other materials that are way lighter. Okay. So I can swing the club faster. Okay. The ball is also different. Okay. The ball is far more far softer. Right. That allows it to stay on the face of the club longer, meaning I exert that force over a greater distance. And then there's a rebound effect that lets it jump off the face of the club. Back in the day, like hitting a golf ball was like hitting a rock, okay? Like it would jar through the club into your hands, okay? Especially if you didn't hit it quite right, okay? And so it was much, much different, okay? That's why now they have to keep adding tee boxes in the PGA, okay? Because holes are just too short, okay? A hole that used to be, like a par 5 is now like a reachable par 4. Okay, guys can drive the green because they're driving the ball 380 yards. Okay, whereas 20 years ago, a guy that could hit it 280 was big time. Okay, technology is just better. All right, it's just way, way better now than it used to be. All right, and so that's kind of those ways. So most sports have embraced that at least in some way. Okay, where they've changed, they've allowed technology to advance the sport, okay? The exception being baseball, okay? A Louisville Slugger is still a chunk of tree, okay? Unless it belongs to Barry Bonds and then it's corked because he's a cheater, okay? Or the other sports science that baseball has embraced. Yeah, their focus is more biological. Got a few roid monkeys in the game, okay? Yeah. I'm just saying. I mean, all the sports are doing that. They just got caught. That's all. Yeah, but there's a lot of roid monkeys out there. Okay, that's another sports science, but not to do with physics.
So for like, let's say you're like Happy Gilmore, the way he swings, would that like actually help the ball go further?
If you could hit it, yes. If you've ever tried to hit it the way Happy Gilmore does, it is really, really hard. Okay, like I worked at a golf course when I was in university, like And we would try that at the driving range all the time. We tried a lot, actually. And it's really hard to make that connection because you have to keep your eye on the ball while you're moving, and most of the time you hit it with the club face wide open and it just slices off. It's Oh, I've seen guys who have hit it and they'll drive it beyond, like they'll land it beyond the end of the range, and the range is 400 yards, right? So yeah, if you can get it right, yes, that is an incredible way to hit the ball because you're using, the club's moving a lot faster, right, than you could if you were, but control is completely out. Yeah. Yeah. All right. All right, so now often several forces will act on an object simultaneously. Okay, so more than one force acting on an object is what happens most of the time. We're just concerned with the net force, the vector sum of all those forces. Sometimes it's simple. Sometimes they're collinear, like in this one here. Force 1 is obviously bigger than force 2, so this object's going to accelerate to the right. Okay, but sometimes, okay, you could get a situation that might be like this. So I've got this box sitting on a level surface, but I'm pulling it by a rope. Okay, I'm pulling it that way, slightly upwards. Okay, friction would be resisting this way. What other forces would be acting on this box? Yeah, there'd be gravity acting on this box. Okay, so this would be the force of friction, and then what would this be? Yeah, this would be Fn, the force of the table or floor or whatever it is. Okay, and then this would be my applied force. Okay, me pulling this direction. Well, what I would have to figure out is what is the net force here? Okay, which would involve me doing this. Okay, I would have to go, all right, so I've got Fg, and then I've got Fn. All right, well, those cancel, so that's good. I probably wouldn't even bother putting them on a free body diagram, right? Or on a vector diagram, sorry. Okay, so our free body diagram, which is this one, identifies the forces. The vector diagram finds us the net force. I'm going to show you. Okay, so I've got normal force here, I've got gravity there. Okay, those kind of cancel each other off, right? Then I've got the force of friction going, the force of friction going backwards, and then I've got this force, that diagonal force. Well, that diagonal force has both a horizontal component as well as a vertical component. Okay, here's where that normal force thing that you were talking about comes into play. Okay, this is getting pretty complex, but okay, if I include again all those forces, okay, so here's gravity. Normal force would actually only come back about this much because I'm also pulling slightly upwards with my force. It was angled. Okay, so there would be this vertical component here. Those all add up to 0. Okay, so I've got those. Then I've got the horizontal component of my pulling force and the force of friction. All right, well, that leaves me with that much net force. Okay, everyone with me there? We wouldn't normally draw a vector diagram with like that many overlapping collinear forces. We kind of just figure it out, okay? But that's where we're kind of headed, okay? Being able to draw a free body diagram and then put those forces in a vector diagram is probably the most important skill, okay? At least in getting started on a Newton's second law problem, okay? So you're always going to have two diagrams. Free body diagram, that'll be like your givens. Okay, and then you'll have the vector diagram, which will be helping you to get your net force. Do you always need a vector diagram? No. Okay, you don't always need a vector diagram because sometimes they're all collinear and you don't need to bother drawing them. Okay, draw the free body diagram and then just calculate. All right, so in Newton's second law, the net force is only one of two factors that influence the object's acceleration. Mass is the other. All right, so if I've got this situation here, or I've got this guy with a golf club, okay? If he swings the club as hard as he can exert a force of magnitude and direction F, okay? In the first situation, he applies that force properly to a golf ball, right? The golf ball is an incredibly small mass. As a result, it will have an incredibly large acceleration. That's what we see here in the way they've diagrammed this. His force applied to a small mass results in a large acceleration. Okay. Then for some reason he decides that a golf ball is not enough of a challenge. He's going to wind up and smoke this truck. Okay. So he's going to swing as hard as he can and apply this force to now an incredibly large mass. Obviously the club will be destroyed, okay, what will happen to the truck? Well, if it was sitting on perfectly frictionless surface, it would accelerate as long as the club was pushing on it, which wouldn't be very long because the club would break. But okay, it would accelerate at least for that instant where the club made contact with the truck. Okay? Now, obviously there are no perfectly frictionless surfaces, so in reality, when he hits this truck, the truck isn't going to accelerate, is it? Not as a unit. Okay, the truck is not going to move forwards. Is he still going to accelerate the matter in the truck? Yes. Okay, if I am standing at the front of the truck and I've got my headphones on and I can't hear anything, as long as I have my hand on the front of the truck, do I know when he hits it? Because I'll feel it. Okay, the vibration will travel through the truck. That means he accelerated every particle in the truck, just not all in the same direction. It didn't result in the truck moving as a unit, but it did result in an acceleration of the mass of the truck. Okay, and it will also result in a change in shape of the truck. All right, there will be a dent. Okay, that part of the truck certainly accelerated more than other parts of the truck because he did some damage to it and changed its shape. That still counts as an acceleration. All right, everybody with me on that? All right, so when a net force acts on an object of whatever mass, the acceleration is directly proportional to the force. Okay, so this is kind of Newton's second law explained out. Okay, so when a net force acts on an object, okay, the acceleration is directly proportional to the force. So if I double the force, I get double the acceleration. If I quadruple it, I get quadruple the acceleration. Okay, it is also inversely proportional to the mass. Okay, so if I double the mass I'm exerting that force on, I'll get how much acceleration? Nope, half. It's inversely proportional. Okay, I double the mass, I've got twice as much mass to move with that force, I'll get half the acceleration. Okay, now this is going to be over 2 weeks worth of this unit. F net equals m times a, 3 variable formula like v equals d over t, and we're going to spend like 2.5 weeks on this thing. Okay, why? Because it's never that simple. Okay, remember that net force, there's 2 ways to calculate net force. You can multiply mass times acceleration like we've done here, but the other way is that it is the vector sum of all forces. So most of the time, you've got to find F net by taking into account all the forces that are acting in a situation. That's why we need so much time on this. We need to be able to look at a wide variety of situations where Newton's second law applies so that we can see how forces interact, okay? How we can add them up, how we can find the vector sum of all these forces. There's a lot of things that just require experience, okay? So we spend a lot of time on Newton's second law because of that, okay? In every Newton's second law problem we do, or just about every one, we'll have to use both of these things. We'll have to find the vector sum of all forces, and we'll have to use m times a. Okay, so a question could say something like, what's the acceleration of a 15 kilogram car that's being acted on by these 2 forces? So then I do the vector sum, and then I find acceleration using this formula. Or it could do it the other way. It could say the acceleration of this 1500 kilogram car is this much. The force applied forward is this much, find the force of friction. So then I would have to find the net force and then use that with the other forces I know and find the missing force. Okay, it's really like one or the other. Okay. And right now that probably doesn't make sense, but it will when we start going into these. Okay. All right, units for force. Said before that units for force are in Newton, but when I'm calculating net force, I'm going mass times acceleration, which means kilograms times meters per second squared. So a Newton is a kilogram meter per second squared. You never have to write it that way. You can mercifully just write it as a Newton, okay? But do you understand that the fundamental units of a Newton are a kilogram meter per second squared? Okay. Anybody need that one anymore? All so we talked about free body diagrams here. Okay, we don't draw them like they did here in A. There are actually two ways to draw free body diagrams, but we never do it that way. Okay, we always draw the forces as though they act from the center of mass. Okay, and we use that term. Okay, in physics, center of mass. A more layman's term is center of gravity. Okay, the reason we don't use that term is gravity is not always involved. Okay, so center of mass is the term that we use. We imagine that all the forces acting on an object act from the center of that mass. Obviously, in reality, that's not the case. Okay, if I get a force that acts just on my shoulder, I tend to rotate. Okay, because that's not acting at my center of mass. That's the reason why in most sports, okay, you want to have a position where you do what with your center of gravity? Stay low. Okay, by lowering your center of gravity, you are more stable. Okay, that's why so many sports involve having your knees bent and about feet shoulder width apart. You're much more stable in this position because your center of mass is lower. Okay, if you're standing upright like this, you're much easier to tip over because your center of mass is higher. Okay, same idea with like why taller vehicles tip over and roll more. Okay, their center of mass is way above something that would be lower. Okay. All right, so force Fg. So when we're writing forces, we typically just use a subscript letter to explain what force we're talking about. So Fg would be the force of gravity. They call this force reactive. We usually call it force normal. Okay, it is the reactive or normal force of the surface pushing back. Okay, friction. Okay, usually F, little f. Okay, we sometimes have applied force. That would be Fa. Okay. If it's a rope and we're pulling on it, okay, we sometimes use Fa, or tension, because it's the tension in the rope, okay, things like that. Right, so basically that's how we write our forces. All right, so since we've already talked about free body diagrams, we're just kind of just go past this here, but just remember those are going to be like your givens, okay, for this unit. Okay, so here's our first and fairly simple Newton's second law problem. Okay, so I have these people pushing a stalled car, which was much more common when I was in high school than it is now, because back then, if your battery was dead, you could push your car and start it on compression, as long as it's a standard. Okay, if it's a stick shift, you can do this. You can't do it with an automatic unless you can push it more than 30 kilometers an hour. Okay, which is a neat trick. Okay, it's also much harder on an automatic transmission to slam it into gear while it's rolling. Okay, whereas with a standard transmission, you could easily do that. You just need a couple buddies who could get your car moving, throw it in second, pop the clutch, and it would fire right up. Okay, what's that? It gets the motor turning. So if you can get the car rolling and then you throw it in gear, okay, the rolling will actually get the pistons moving. Okay, and it'll compress the gas without you having to use the starter to turn the pistons. Right? When you use your starter, you actually use an electric motor to crank the pistons until they ignite and compress enough fuel to start. Okay, this means I get them moving by mechanical energy instead of electrical. Well, the transmission works differently, right? Yeah, and it's not good to throw it from neutral into drive. Okay, it makes this crunching sound that's usually kind of bad. Okay, popping the clutch engages the transmission more slowly. Yeah, the clutch you wear a little bit. I mean, the clutch wears all the time. So, okay, but that's back in the day. Can't do that anymore. All right, anyone in here actually drive standard? Wow, that's like one of the highest numbers I've seen in a long time. Most people don't even know what it is. I had a buddy who took his car in to get an oil change the other day, and they wanted to drive it in. They wouldn't let him drive it in, and then they sent a guy out, said, "Can you drive it in?" Because none of them could drive standard. No one could drive it into the oil change. Okay, now that we've gone way off topic. Okay, so to start this problem, the first thing I want to do is draw a free body diagram. All right, so I'm going to represent the car with a box. Okay, and that box, I'm going to put the mass inside that box. It's 1,850 kilograms. Now I'm going to draw the forces acting on the car. Okay, I can put gravity on here if I want to, and the normal force, but here's the thing about those two forces. They'll cancel. So they're not really important in this question, okay? So I don't necessarily have to draw them on there. I certainly wouldn't mark it wrong if you didn't bother to put those forces on. Since the car is not accelerating vertically, they're not all that important, okay? The forces that are important are the two people pushing, okay? So one of them is using 275 newtons. The other one is using 395 newtons. And then there's a force of friction of 560 newtons. All right, so I've drawn my free body diagram. There are three forces that are important. I need to find the net force. How do I find the net force? Okay, I can do that, but I don't have the acceleration right now. Okay, that's what the question wants me to find. So I can't use that method. The other method is to find the vector sum of all the forces. These forces are all collinear, right? They're either forward or backward. Is it pretty easy to find their sum? Yeah, okay. All I have to do is go negative 560 plus 275 plus 395. Okay, I think that comes out to 110, right? So I've got a net force of positive 110 newtons or 110 newtons forwards or right or whatever. Okay, so I've got that. Now I can use this formula because I have F net and I have the mass of the car. Now I can find the acceleration, F net over m. So I take my 110 newtons, and I divide that by the mass of the car. This is a pretty small acceleration. Yes, it is. Okay, you don't get a car really flying, okay, by pushing it. Right? So we've got 110 divided by 1850. All right, so this is like 6 centimeters per second squared is my acceleration. But if I keep pushing, that adds up. Okay, it'll add up because every second I push, it'll go 6 centimeters per second faster. Okay, and eventually I'll get it to the point where the person can get it going. Okay, all right. So we're going to have 0.056 meters per second squared, or we could say 5.6 times 10 to the minus 2 meters per second squared, and that would be forwards or positive or something like that for our vector. Okay, every Newton's second law problem you do is essentially going to break down to these two steps. Okay, the part that becomes more difficult is the vector sum of all forces part. Okay, we just start throwing in more and more situations where the forces are acting in all different directions, and we're trying to find out what their sum is. Okay, but for all of them, you're going to be doing the vector sum of all forces and F equals m times a. Not always in that order. Okay, sometimes you'll do the F times a or m times a first. Okay, and then figure out one of the forces or something like that. Okay, but it's always going to break down to these two steps. They're always going to be involved in a Newton's second law problem. Okay, so when we do that, okay, typed out, it looks a little better. Okay, but that's what we did. Sorry, was it 5.9? Did I do that wrong? Sorry, it's 5.9. I wrote 5.6. I don't know why I did that. It's 5.9. Okay. All right. Questions there? All right, we'll leave it there for today, and tomorrow there won't be a quiz. I haven't taught you enough in this unit to quiz yet, okay? But we'll be spending a lot of time looking at different Newton's second law situations.